chapter 4 on traveling wave in transmission line. Okay, related to transient phenomena. Okay, by this topic, we can understand the power surge in a power system and determine the end voltage by using Bewley lattice method. By the way, Hidayu, where you graduated from? University.
UiTM Shah Alam, my degree.
Yeah. Power or electronic?
Electrical power.
Power. So you know about this one? Bewley lattice method. You have, I think you should have a HV class, right?
HV class, for one sem. Only one sem HV class.
Who's your lecturer?
Tak ingat dah sekejap.
Because
Dr. dia perempuan.
Her name?
Her name, I forgot. Dr.
UiTM Shah Alam?
Ya, itu Shah Alam.
UiTM Shah Alam, HV.
Tak ingat lah. Tu dah.
Tak pernah lupa pula orang UiTM. Okay, because in UMP we don't have a pure HV subject in undergraduate. Our HV subject is combined with power system protection. So it's not detailed enough, and this topic was not in the subject in the degree. So that's why I put it here in our master class. Okay. Okay. By the way, if you took communication, maybe communication lectures, maybe you also will use this one, Bewley lattice. Okay. Right. Okay. As you know, high voltage surge induced on transmission line is due to can be direct stroke from maybe lightning from direct stroke or indirect stroke. Lightning will not directly strike the transmission line or switching operation. Okay, so all of this force will generate surge voltage. What is surge voltage? Okay, for example, if we have AC, then the lightning strike at this time, then the voltage will rise up. Okay, so it will become like this. So over the limit of our nominal voltage. So this is surge voltage. So this surge voltage will travel along the line at the speed of light. Okay, because actually it's not speed of light. It depends on the material of the transmission line. Okay. As they reach the end of the dimension or junction of the line, they will partly reflected or transmitted. Okay, you can imagine if we hold a rope. Okay, this is a rope. Okay, on the left side is untied. This one untied. This one tied to this wall. Okay. Okay, if it is untied, then we shake the rope. Okay, shake the rope, so we will create a wave. Okay, it will generate wave from here, and the wave will move. Okay, in the end, it will disappear. Okay, will disappear. No reflection. But if we tie it to the wall, okay, the wave will travel and will return to our hand. Okay, maybe not fully return at the initial heights, okay, at the initial height here, maybe partially it will come back. Okay, so that's the idea, the traveling wave. So there are two waves here. Okay, this is the incident wave, the original wave. Okay, there are incident wave, original wave, okay, and reflected wave and transmitted wave. So transmitted wave will imagine this is the junction. Okay, we have two connection here. Transmission line with impedance Z1 and Z2. Okay, it can be transmission line, it can be a two system, okay, circuit system. So if the impedance not matching, okay, this Z1 doesn't equal to Z2, so this will happen. Some will be transmitted and some will be reflected. Okay. Okay. Reflection of traveling wave at a junction. Consider a step voltage wave of a magnitude E incident at junction J between two lines of surge impedance Z1 and Z2. Okay, refer to this figure. This is the junction. A portion ET of this surge will be transmitted. That's why it's T here, and portion of ER will be reflected. This is for reflected wave. Know this continuity of potential at junction J. Therefore, E, the incident wave, plus ER equals to E transmitted. Okay. Now this discontinuity of current at junction J, therefore I plus IR equals to IT. Okay. The incident surge voltage E is related to the incident surge current. Okay, this is Ohm's law. E equals to I Z. So you can see the similarity here. Okay, by the surge impedance Z1. Okay. Similarly, the transmitted surge voltage ET is related to the transmitted surge current IT, okay, by the surge impedance of Z2. And the reflected surge voltage ER related to surge current IR by the surge impedance Z1. Okay, let's look back at the figure. So you can see here, this is IR1, ER, and Z1. Okay, and from for this side, ET, IT, and Z2. So we can we have three equations now. However, it is to be noted that the reflected wave is a reverse wave. Okay, so it's not in the same direction with the incident wave. Okay, incident wave junction here. The reflected wave, E reflected. Okay, you see the different direction. Okay, this one is the same direction with the E here, E transmitted. So the direction here is negative, so we put negative for reflective part. Okay, so we substitute all of these individual equation into this current equation. This is what we have. Okay, so then the equation can be simplified into the following reflection ER wave equation. Okay, so we arrange this one. We get ER equals to Z2, Z1, the junction J. Okay, so we have this one, Z2 minus Z1 over Z1, Z2 plus Z1 times E. Okay, and then similarly to the transmitted wave, ET equals to 2 Z2 over Z2 plus Z1 times E. Okay, so we take this out, this part out, and we put it as alpha, and this one is for beta. Okay, it's like a coefficient, reflection coefficient or transmitted coefficient for both wave, for reflected wave or transmitted wave. Okay. Reflection and transmission of wave at a bifurcation or two junction. Okay, suppose we have one original line here, and at one junction it's terminated to two into two transmission line. Okay. And the transmitted power or currents will be different if the Z is not the same. This one is Z1, Z2, Z3. If all these two is not the same, so the current will not be the same. Okay, if Z2 equals to Z3, so the current or power transmitted will be the same. Okay. Okay, let's take a look at this example. We have one traveling wave with peak voltage at 25 kilovolt. Okay, we have one original line, overhead line A with impedance 450 ohms, then split it into three other lines at this junction J. Okay, B, C, and D. So we see here the impedance of B and C is the same, while D is different. Okay. So here we need to calculate the magnitude of voltage and current wave which are transmitted and reflected when the surge reach the junction J. Okay. So for this example, we neglect the attenuation of the wave. Okay. Okay. So firstly, determine the parallel equivalent impedance after the junction. So we can see that 600 is parallel with 600. Okay, this is B, C, and D. And after calculation, we got this one. So this is after the junction. Okay, ET equals to 2 times 50 times 25 over 450 plus 50 equals to 5 kilovolt. And for reflected, E reflected equals to 550 minus 450 times 25. Okay. So let's look back. The 450 is the impedance of this A, and the peak voltage is 35 kilovolt. So here we use the equation given earlier. this equation, okay, to determine the reflected and transmitted wave voltage. So the transmitted voltage is 5 kV and reflected wave voltage is minus 20 kV. Okay, and you see the wave that comes reflected back to the source. Okay, and then we can determine the current uh, the original I and reflected current. So using the equation given. And finally, we can calculate individual currents for each transmission line.
Doktor,
Ya.
untuk current tadi guna formula yang sama kan?
Ya. Okay. Reflection of traveling wave at the junction open-ended transmission line of surge impedance Z naught. Okay, so it's open-ended. And short circuit end, we just put short circuit here. Okay, ada dua case. So we have two case here. For open-ended and for closed-ended or short circuit condition. Okay, this is open-ended and short circuit ended transmission line. So when switch S is closed, the voltage and current wave of magnitude V and I respectively travels towards the open end. These waves are related by this Ohm's equation. V over I equals to Z, and the electromagnetic energy, electrostatic energy stored by the element dx are given by this equation 1 over L dx I square and 1 over C dx B square. Okay, for your information, a transmission line consists of this element, a combination of this element R, L, and C. Okay. Okay. Because you can imagine this is the cross section of a transmission line. Is a coaxial configuration. Okay, imagine that the transmission line is a power cable with coaxial configuration. This part is metal, copper. Okay, the outer part, this is the cover of the cable. Okay, this is copper. And this one is the insulation. Usually it is XLPE material or cross-linked polyethylene. Basically, it's a polyethylene which treated polyethylene to improve the breakdown strength of the material. Okay. So inner part usually will be connected to HV. The outer part is to ground. Okay. So from here, we should be able to understand that this configuration is actually, if we put into circuit, it will be this one. Okay, because this is high voltage part, this is ground. So we should understand that when we have high voltage part, so means that we have positive charge. Okay, and this is the ground, so it will attract negative charge. So between this will be electric field. Okay, this is electric field. So when we have this idea, we should put capacitor here. Okay, means that this is HV, this is ground. Okay, and furthermore, the current will flow through this high voltage conductor in the middle here, the inner conductor. So when current flow, there will be power loss. So when there is power loss, we put P equals to I square R. We put resistor. Okay, and when current flow, also there will be electric field. Magnetic field. Okay, due to current flow. So this is the symbol, the inductance. Okay, it's a continuous because we don't know, we don't have resistor, inductor, or capacitor one by one like what we understand. Okay, it's not resistor like this, no resistor or a coil like this in the transmission line, or a resistor is line like this in the transmission line. So it's a continuous component. So that's why we take dx, which is a small portion of this transmission line. Okay. Okay, it's called lamp element. Lamp element. You can Google what is lamp element. Lamp element model. Okay. Okay. So that's why we have two form of power. The power in terms of L, where we consider L, okay, the stored energy in L, the inductor, and the stored energy in the capacitor just now. Okay, since the current at the open end is 0, because it's an open circuit, consider open-ended transmission line. So it is a open circuit. Okay, open circuit. Okay. The electromagnetic energy vanishes and it transforms into electrostatic energy. Okay. Okay, for an electromagnetic energy to appear, the current must flow. Now the current cannot flow, so all of the charge will be at the open-ended. Okay, when it's open-ended, that's why I said to you just now, we can imagine it as a capacitor. Okay, so it's like we have capacitor here. The current cannot flow. Okay, so everything will be electrostatic energy. Okay, as a result, that the change in voltage is E. Okay, power due to electromagnetic energy equals to the power of the electrostatic energy. Okay, V is E. Okay, so we can cancel this one. Okay, leaving this part, and finally get this one. Okay, so we have two, this one and this one. Okay, this means the potential at of the open end is raised by V volts. Therefore, the total potential of the open end when the wave reach this open end becomes V plus V. So it becomes 2V. Okay. So originally it is this height. So 2V become double the height. Okay, that's for open-ended. So this is how we imagine how the wave move. Okay, originally this is the original the source. This is the end, the open end, and the original voltage is E here. So the wave will travel from the source to the open end. Because it is an open end, so the wave will be double here. So it will be reflected back, and the height here is 2E. Okay. Okay. However, reflected current side is reversed as the open end is open circuit, so no current can flow beyond that point. So no current will return back. Okay, all will be transmitted. At the instant the reflected wave reach the source end, the distribution along the whole line will be 2E and current 0. So no current here. Okay, this is V, this is I curve. Okay. At this generator or at the source, the voltage is held by the source to value E. Okay, it follows that there must be reflected voltage of minus E, and associated with it, there will be a wave current of negative E. Okay. After the original voltage reflected at the open end and reach this voltage, reach the generator or the source, it must uh, held by the E value. Okay, voltage here will be E value, so a negative voltage will be reflected. Okay, to held the E value. So it will travel to the open end again with the current of negative I. Okay, and again when the voltage negative E reach the open end. Okay, so it reach the open end here. So the total here will be a sum of all of this. Okay, so it's 2E minus E. So this is what left. Okay, it's only E with current negative I. The reflected wave due to this will be negative E and positive I. And when this have traveled to the generator, they will have wiped out both voltage and current distribution, leaving the line for an instant of its original state. The voltage at the source, okay, the voltage at source N cannot be more than the voltage V. Therefore, a voltage of negative V and current wave of I is reflected back into the line. So finally, nothing left here. Okay, so this one they started the E again. And reflected as negative E, and current is the opposite. No, because it's open end, no current will be reflected. And finally, when this one reaches the source again, then the voltage will be sum E minus E is 0. And then the cycle will be repeated again. Okay, this is a traveling wave in open circuit condition. And this is a summary at different time. Okay. T equals 0, T equals the L. Okay, this is the L, the length of the transmission line. Okay, then 2L. Okay, reflected here. So this is at source. Then traveling wave move back to the open end, and so on until finish. Okay, you can read this one. This is what I explained just now. Okay, for short circuit ended. Okay, short circuit source line, then short circuit. Okay. So the voltage and current relationship is still the same, V over I equals to Z, and the stored energy originally is the same, but here is a short circuit, so we don't have this electrostatic part because no capacitor is charged. So all of the electrostatic energy will be transformed into electromagnetic energy. Okay, so the change in current is I. So finally here what will happen is that the current will be double. The current will be double for short circuit condition. Okay, for open circuit the voltage are double. Okay, and the transmission the wave, the transmission wave will follow similar traits as in open circuit condition. So this is the summary for short circuit. Summary of traveling wave in short circuit condition. Okay, so we skip this one. Okay, that's the end for the first part of this chapter.